Hello everyone. So this is Moshmi with yet another problem on oscillations. So this question was sent to us and hopefully you all will be sending more such questions and we shall be trying to give suitable explanations to it. So let's begin. An ideal gas is enclosed in a vertical cylindrical container and supports a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area A. Atmospheric pressure is P0 and when the piston is in equilibrium, the volume of the gas is V0. The piston is now displaced slightly from the equilibrium position. Assuming that the system is completely isolated from its surroundings, show that the piston executes simple harmonic motion and find the frequency of oscillation. So, we have an ideal gas which is enclosed in a vertical cylindrical container and it supports a freely moving piston. The mass of the piston is given as m. Now, the piston and the cylinder both have equal cross-sectional area of A. And atmospheric pressure is P0. When piston is in equilibrium, the volume, in fact this is the initial volume which is V0. And then the piston is given a slight displacement. Now we should start assuming that the system is completely isolated from its surroundings. Now when a system is completely isolated from the surroundings, it actually means that the pressure and the volume, they will be related to each other by the adiabatic relation. So let's begin with that note. We have the pressure and volume related as PV to the power gamma is a constant. Now, here gamma is a ratio of the specific heats. So, it is nothing but the specific heat at constant pressure to the specific heat at constant volume. So, this is gamma in fact. Now, here the initial volume here is V0 and the total pressure, let's assume that to be P and it's nothing but equal to the atmospheric pressure plus or the sum of atmospheric pressure and the pressure exerted by the piston on the gas. So the piston will exert some pressure on the gas. It's that pressure that we need to include here. Now, what is the pressure exerted by the piston on the gas? That will be the force per unit area. So, the mass of the piston is m, the force is mg and divided by the area. The area is A, which is the same for the cylinder as well as the piston. So, this component is in fact the pressure exerted. So, this component indicates the pressure exerted by the piston on the gas. So we have the net pressure in this form. Now the piston has been given a slight displacement from the equilibrium position. So let us suppose that the piston is displaced from the equilibrium position through X, and when the piston gets displaced, what's going to happen? Both the pressure and the volume, they will change. So let us assume that the change in pressure is delta P, while the change in volume is given by delta V. And we know what delta V is. The change in volume is nothing but, or we can write this as area times the thickness. So the area here is A and the thickness or the displacement in fact of the piston is X. So this is in fact the value of delta V. Now let's proceed with the same relation. Since this is constant, so the initial and the final conditions, the product in this way will be the same as it's a constant. So the initial part, we have the initial pressure as P, the initial volume as V naught to the power gamma, and this is equal to the final part. That is, we know what the final pressure is. This was the total pressure and the change in pressure was delta P. So we have the final pressure as P plus delta P, and the final volume, here this was the initial volume and the final is V naught, that is the initial thing, plus the change in volume, that is delta P, and we have this power gamma to it. So now let's break this off, or let's imagine that we expand this part binomially. So we have P V naught to the power gamma is equal to P plus delta P. Let's keep it in this way for some time. And working on this, we have this as V naught taken common. We get this as 1 plus delta V by V naught, and this is whole to the power gamma. So let's work on that. So left hand side we have P V naught to the power gamma. Then breaking that part up, let's keep the first term as it is. We have the second term as V naught to the power gamma, and the third part we expand that binomially. So this is as if 1 plus x whole to the power n. So expanding this binomially, we use the relation 1 plus x whole to the power n as 1 plus nx plus further terms will follow, but we neglect the higher order terms as they will be very small. So let's keep only the first two terms here. We have 1 plus n, n is gamma, and x is delta V by V naught here. So let's work on this. We have P V naught to the power gamma, and let's take P out from the first expression. We'll be left with P times 1 plus delta P by P, and we have the other terms following. This is 1 plus gamma delta V by V naught. So you can see that P V naught to the power gamma gets cancelled out on both sides. So this is what is getting cancelled out. Let's continue with that. We have 1 here, and this will be equal to 1 plus delta P by P times 1 plus gamma delta V by V naught. Now let's break this up. We have 1 equals, this is 1 plus gamma delta V by V naught plus delta P by P plus the second and the fourth term, that is gamma delta P by P times delta V by V naught. So you can see that for the first term, this is getting cancelled out with the left hand side. We are left with the second and the third terms, but looking at the fourth term, as it includes delta P and delta V, both of which are very small. So the product of them is still smaller. And so this entire fourth term on the right hand side may be neglected, as it will account to a very small value. So now let's see what's left. We have gamma delta V by V naught. This is equal to minus delta P by P. So let's find out the change in pressure or the excess pressure in fact. So we have delta P as equal to minus of gamma P delta V by V naught. So this is the excess pressure or the change in pressure that we have. Now, the restoring force set up here. Let's take the force to be F. We know force is nothing but pressure times the area. The pressure, let's look at the pressure. We have the pressure, the change in pressure as delta P times the area, that's A. So we work on this. We have F is equal to, this is delta P, let's put in the value, gamma P, we have an A coming up here, delta V by V naught. Now, we knew that delta V was equal to A times X. Let's use that here. So, we have, putting this value of delta V here in this relation, we have this as minus gamma P by V naught, and A is nothing but, or delta V is nothing but AX. We have A square coming here and an X. So we have minus gamma A square. So this is minus gamma P A square by V naught times X. So let's work on that. We already know the value of P. Let's put it and see how the equation looks like. So force will be equal to, this is minus gamma A square by V naught. P here is nothing but equal to, we have the pressure, the net pressure as P naught plus mg by A coming up, and we have an X here. So this is in fact a wonderful equation. Doesn't it resemble the equation? F equal minus kx. So yes, you are right. This is representing the equation of simple harmonic motion. Where the force constant or the value of K may be given as minus gamma A square by V naught times P, which is P naught plus mg by A. So this is the equation of simple harmonic motion in fact. So now if you try to work this out, you have the value of K now, and finding out the frequency of oscillation for simple harmonic motion. We already worked out the original formula. Let's use that here. So we have the frequency of oscillation. Let's take that to be n. N is equal to omega by 2 pi. So we have 1 by 2 pi, and this is equal to K by M. So let's put in the values. We have N equals, okay, that's capital M in fact. As given in the question, it's capital M. So this is capital M. Sorry for this. We have 1 by 2 pi, and this is root over K. We have the value of K now. That's minus gamma A square. Now this is the big value of P here. That is P naught plus mg by A by, we have V naught here and an M coming up. So this is in fact the frequency of oscillation of the piston. So a wonderful problem. Do keep posting many such other problems and enjoy the solutions. Thank you.